All right, today we are diving into a really cool question in AI. It's all about how these systems learn from their mistakes, and more importantly, how they got so incredibly fast at it. Let's get into it. So to really get this, I want you to picture learning to ride a bike. You know the drill, right? You wobble, you fall, you figure out, okay, I leaned too far that time. That memory of why you fell is the whole game. But now, what if every single time you fell, poof, that memory was just gone? You'd be stuck falling over and over with no clue how to fix it, right? You'd never get better. And that right there was the huge problem for the first AI learning algorithms. They were literally stuck in that exact loop. Try, fail, forget. Try, fail, forget. And as you can imagine, making any kind of real progress was just painfully slow. And this whole situation, well, it has a name: the learner's dilemma. It's that core problem of how do you learn from what you've done if you can't even remember doing it? So the first way they tried to solve this was called on-policy learning. And honestly, it was not great. Super inefficient. Think of it like this. The AI tries something, gets data from that one attempt, makes one tiny little change to its plan, and then it just throws all that valuable data in the trash. I mean, it was a safe way to learn, sure, but man, was it slow. So you can see the problem. And the first huge breakthrough came from a really simple but kind of brilliant idea. Wait a minute, why are we throwing away all this data? Why can't we just learn from the past? Instead of the AI just glancing at its notes and then checking them, what if it could actually sit down and review a video of every single thing it's ever tried? That's the big idea behind something called off-policy learning. And the promise here was huge. It can make the AI way more data efficient. Basically, it could squeeze a whole lot more learning out of the same amount of practice. Now, there's a pretty clever mathematical trick that makes this all work, and it's called importance weights. All it really does is let the AI look back at an old memory and ask a simple question. Okay, based on what I know now, how likely is it that I would have made that same move? That little calculation is key. It helps the AI figure out how much to trust the lessons it learned back in its rookie days. But, and there's always a but, isn't there? This powerful new technique had a really dangerous side effect. Because think about it, what happens when the advice you're getting from your rookie self is just totally wrong for the expert you're trying to be? See, with that old slow and steady method, yeah, it was boring, but it was stable. You'd get this nice, gradual, predictable progress. Nothing flashy, but you knew it wasn't just going to blow up on you. Then, when we start reusing all that old data, at first, things look incredible. The AI is learning way, way faster. Why? Because it's making hundreds of these little learning updates. They're called gradient steps on the same chunk of experience instead of just one. And then this happens. A complete catastrophic collapse. The AI basically gets greedy. It starts listening way too much to that outdated advice from its past, and its performance just completely tanks. It falls right off a cliff. And here's the reason why that happens. The AI is trying to optimize its strategy based on moves that only seems like a good idea for its old, kind of dumb self. As it gets smarter, that old advice doesn't just get irrelevant, it actually becomes toxic to its learning. So that's the puzzle, right? How do you get all that speed without the risk of a total meltdown? Well, the first really smart solution to this is an algorithm called proximal policy optimization. We just call it PPO. And the whole idea is to learn with guardrails. So here's PPO's secret sauce for staying safe. It still looks at old data, but, and this is the key part, it puts a hard cap on how much it can learn from any one single memory. It literally clips the value. It's like the AI is telling itself, whoa, let's not get too carried away by this one thing that happened a while ago. And that simple move prevents it from making these huge, risky bets based on stale information. And the result? It's pretty incredible. Because it avoids those collapses, PPO can safely make about 300 learning updates from a single batch of experience. I mean, think about that. That's a 300 times improvement in efficiency compared to that old method of just learning once and throwing the data away. That is a massive leap. So if PPO had a motto, it would be stability over speed. Its biggest strength is just how reliable it is. And that makes it the perfect tool for situations where getting more data is cheap and easy, like inside a computer simulation. And, this is a big deal because PPO is one of the key algorithms used to train the big language models that a lot of us are interacting with every day. Okay, so that's PPO. Now, let's talk about the next big step in this evolution. If you think of PPO as being really good at learning from the recent past, well, our next algorithm is all about learning from the entire past. It's called Soft Actor Critic, or SAC. Because, see, even PPO is still a little bit wasteful. After it does its 300 or so learning steps, it still throws that batch of data out and gets a new one. So that leads to the next big question. What if? What if we never threw any data away? What if we could build the ultimate AI memory? And that is exactly what SAC does. It uses something called a replay buffer. The best way to think about this is like a giant, searchable library of everything the AI has ever done. Every success, every failure, every single move. And whenever it's time to learn something new, it just reaches into this massive library and pulls out a random handful of memories to study. Now, the reason this whole memory bank idea works is because of a really subtle but super important change in the question the AI asks itself. The old way was to ask, hey, how good is this game state in general? Which is almost impossible to answer when you're mixing memories from when you were a rookie with memories from when you were a pro. But SAC asks a much smarter question. It asks, how good was it to take this exact action when I was in this exact state? And that's a historical fact. It's something it can just look up in its library, which makes the whole system work. All right, so let's tie this all together. We've basically watched AI go from having total amnesia to learning with cautious little guardrails, and then finally to having this perfect ultimate memory. And what we have now is a clear playbook for how modern AI learns so incredibly fast. And it really comes down to a fundamental trade-off. You've got PPO, which uses those clipping guardrails to be super stable and reliable. That makes it perfect for simulated worlds where you can just generate endless amounts of data for free. Then you've got SAC with its massive replay buffer memory bank. It's all about getting the absolute most out of every single piece of data, and that makes it the go-to choice for things like real-world robots, where every single experience is valuable and expensive. And listen, this isn't just some abstract theory. This is real. The source material for this whole explainer points to an actual robot that used SAC, and it went from basically a pile of metal to walking on its own in just 2 hours. That's what happens when you learn this efficiently from every single thing you do. So it's clear AI has gotten incredibly good at learning from its past. And that leaves us with this one really big forward-looking question, right? What's the next big thing? What's the breakthrough that's going to let AI not just learn from what has happened, but to actually imagine and plan and learn from a future that doesn't even exist